Hey folks, all right, let's see here. This is Professor Smartycorn, and I'm going to review some things about the periodic table that you might have missed in class. Okay, first up, I just want to talk about two terms that we learned last class on the Chem Crunch day. Electronegativity. What is it? Well, electronegativity is a way to measure the tendency of an atom to attract electrons. You can think of it as electron-getativity or electron-gravitivity. This chlorine is exhibiting lots of electronegativity. It's really pulling those electrons close towards it. So a high electronegativity number means that an atom has a high attraction for electrons, or an element has a high attraction for electrons. Okay? Electron-getativity or electron-gravitivity is electronegativity. First ionization energy is the other term we learned. Now let's break it down because it sounds a little complicated. Ionization, that means when something becomes an ion. For example, by losing an electron, it could become a positive ion. Energy, well, it's just a measure of energy. First, we'll get to that in a moment. Okay, first ionization energy, it's the amount of energy needed to remove one outer electron from an atom. So that's why we call it the first ionization energy. It's a measure of removing the first or outermost electron from an atom. And a high first ionization energy value means that it's very hard to remove electrons. You have to use a lot of energy to pull off one outer electron. Now here's a diagram that I already showed you last class to sort of explain this idea. Imagine that we've got the nucleus, and that's positive, and then we've got the electrons that are being held by the nucleus. They're negative. Okay, so the nucleus is like a guard, and the electrons are kind of like money. Other atoms might want to steal those electrons. Now, how can atoms have different amounts of first ionization energy? Well, you could imagine that if an atom has an electron way out here, several energy shells out, it might be easier to steal that from the nucleus. The positive nucleus is holding onto these negative electrons, but if the electrons are farther away, it's easier to steal them. But if you have an atom that only has a couple of electrons and they're very close in, it would be harder to pull off those electrons. The positive nucleus can hold onto those negative electrons more easily. They're closer in. So again, different atoms can have different first ionization energies, which is a measurement of how hard it is to remove electrons or one outermost electron from that atom. Again, it's just how much energy to remove one outer electron from the atom. All right, let's have a look at your periodic table that is drawn on page 31. And you're going to want to pause and turn to page 31 because we're going to jot down some notes here. Now, the first part of this should be things you already know. Here we go. These are the metals. Okay, you know that. The left side of the periodic table are the metals. And then there's kind of this dividing line here. And then over on the right side of the periodic table, we've got the non-metals. Okay? Now, here's a new idea. We can say that things that are further in this direction on the periodic table have more metallic character. Now, we don't necessarily mean they're more shiny, but to chemists, metals have certain properties. And so as we head this direction, the elements have more and more of those metallic properties or metallic character. And similarly, we could say that going this direction, they're more non-metallic. Or it'd be more common to say they have less metallic character when we're going towards the right. Okay? Now, that means that over here and actually down at the bottom, francium is the most metallic element of all. It is, again, not the shiniest necessarily, but it has the most chemically metallic properties. Francium is very metal. Okay, so there you go. Now, that dividing line is the metalloids. Metalloids are, for the most part, anything that touches that bold, dark staircase line that goes right here. So we've, but we say that metalloids don't like Alpo dog food because the metalloids don't include aluminum or polonium. Now let's have a look. We've got boron, we've got silicon, we've got arsenic, we've got tellurium, we've got astatine, then we've also got germanium and antimony. Yes, SB is antimony. Don't ask me why. Aluminum would go right here under boron, and polonium would go under tellurium. We don't consider those metalloids. So that's why we say metalloids don't like alpha dog food. Metalloids are anything that touches the bold staircase except for alpha. Okay, now here's an idea that you already learned at the beginning of the year, and it came back on the Chem Crunch, and I want to remind you of it again. Anything in period 2, if you look at its electron configuration, it only has 2 shells of electrons, 2 energy shells, 2 electron shells, 2 orbits. Anything in period 3, this is part of how the periodic table is organized. Period 3 means, oh, we start a new shell. We've got 3 shells. Period 4 has 4 shells. Period 5 has 5 shells. Period 6 has 6 shells. Period 7 has 7 shells. You can just look at the electron configuration of any element, and it should match to the number of shells should match to the period that that element is in. Okay. Another thing that you already know is that these elements in group 1, they all have 1 valence electron. That means it's really easy for them to give up that 1 electron and become a positive 1 ion, a +1 ion. Similarly, in group 2, they've got 2 valence electrons, and they're very happy to give up those 2 electrons and become +2 ions. Okay, that's because 8 is great, and they're trying to become more like a noble gas. Right? Now, over here on the right side of the periodic table, with group 13, 14, 15, 16, and 17, remember, group 17 has 7 valence electrons. Group 13 has 3 valence electrons. But back to group 17. If it has 7 valence electrons, it would really love to get to 8, because 8 is great. And so it's very, very common for these group 17 elements to steal 1 electron from somewhere and then have a -1 charge. And in group 16, they've got 6 valence electrons. They're so close to 8, they can just taste it. So they're very likely to steal or gain 2 electrons from somewhere and become -2 ions. Okay? And that's, again, stuff that we've already learned from the beginning of the year. Now, let's add a new idea here. What does reactivity mean? Well, you probably could guess that reactivity sort of means how much something reacts with other elements. That's essentially it. But to a chemist, what reactivity really means is the eagerness of an element to bond with other elements. And in order to do that, it has to gain or lose electrons. So really, reactivity is how eager is an element to either gain electrons or lose electrons. So let's look at different places on the periodic table. And because the periodic table is full of patterns, there are going to be some patterns to how reactive certain elements are. Okay, so if we go on the right side of the periodic table here, where we're almost to 8 is great, we're almost to a stable octet. If we've got an element that's close to a stable octet, we would say that is highly reactive. And a good example of that would be the halogens in group 17. They have 7 valence electrons. They're very, very close to 8 valence electrons, so they have a strong tendency to gain 1 electron to become more like a noble gas. We could also say that atoms with very few energy shells and 7 valence electrons, they are the best of all at gaining electrons. We would say they have a high electronegativity. Now let's break that down. Atoms with very few shells, the nucleus is very close to the outer edge of the atom. The nucleus is very exposed. That means that positive nucleus can easily pull in 1 more valence electron, and then the atom will have 8 valence electrons and be more stable. So actually, right here, fluorine is considered the element with the highest electronegativity. Fluorine's electronegativity value is 4.0. It's the most electronegative element of the whole periodic table. Why? Because it has very few energy shells, so the nucleus is very close to the outer edge of the atom. That makes it really easy for that positive nucleus to pull 1 more electron in. So fluorine, we can think of it this way. Fluorine is like an electron hog or an electron thief. Fluorine is really good at stealing 1 electron because its positive nucleus is very close to the outer edge of the atom because it has very few energy shells, so it can easily steal 1 electron. So it's the most electronegative element. Okay, now going on to this next bullet point, valence electrons that are easy to remove, like over here, elements with only 1 or 2 valence